Hello and welcome to lesson 3 of this course. In the previous lesson, we looked at all the different kinds of out-of-memory error exception messages that we can see with Java applications. We also looked at what those messages mean and which memory pool we should be focusing on when we get a particular out-of-memory error message. This is how the agenda for this lesson looks like. In this lesson, for all the different kinds of memory problems, we'll go over the required diagnostic data, data collection and analysis tools, and how these can help us resolve the memory issues. In the first section, we'll discuss how we can diagnose and troubleshoot Java heap related memory problems. In the second part, we'll talk about diagnosing out-of-memory error exceptions arising due to the use of finalizers. And then we'll learn about troubleshooting the permgen and metaspace related memory issues. In the third and the last section, we'll look into the code cache and native memory related out-of-memory errors, and we'll take a deep dive into troubleshooting those problems. Let's look in detail what we should be doing to troubleshoot memory leaks in the Java heap. The first thing we need to do while diagnosing memory problems is to confirm if we are really facing a memory leak. Rule out the possibility that the heap is sized too small and the live set of the objects is not able to fit well into the configured Java heap. We can do that by monitoring the Java heap usage over time. If the full GCs are not able to claim any space in the old gen of the heap, then it might just be a configuration issue. Try increasing the heap size and run the application again. If the memory growth or the out-of-memory error failure still persists, then it is most likely that we are dealing with a memory leak. It's also important to monitor and understand if the heap usage growth continues even after the application reaches a steady state. Please note that the memory usage growth during the startup or warm-up of a process is normal. Let's take a look at a couple of examples on how the heap usage can be monitored. These GC logs show that the old gen is completely full and the back-to-back full GCs are not able to free up any space in the old gen. So in this case, we should first try to increase the Java heap size and test the application to see if the increased heap size resolves the problem. Visually monitoring the heap usage with tools such as JConsole, also used in this snapshot, helps us to understand if we might be having memory related issues with respect to the Java heap. This snapshot shows that the overall memory usage of the process is continuously growing over time. And this chart shows that the memory usage in the old generation is growing over time. So for such scenarios, the first thing we should try is to increase the heap size using -XMS option. We recommend setting -XMS, initial heap size, equal to -XMS, so as to avoid unnecessary overhead due to the expansion of heap at the runtime. Let's see what diagnostic data we should be collecting once we have confirmed that we are most likely dealing with a Java heap memory leak. GC logs. GC logs can help us see the heap usage details, tell us if there are any long GC pauses during the application run, and thus help us appropriately configure the memory pools. Heap dumps are the most important data for troubleshooting memory leaks. Heap histograms. Heap histograms provide us a quick view of the heap and help us understand what's growing in the heap. Java flight recordings contain detailed information about the GC events and can also show us the memory usage changes over time. Now let's spend some time learning about the GC logs. GC logs are very useful in determining the heap requirements and in letting us see if there are any long or excessive GCs during the application run. These are the GC logging options that we can use in the production systems with JDK 9 and with the prior Java versions. For Java 9, we can use the new logging option, -xlog. This GC log entry shows that the full GC is collecting the Java heap, but it fails to reduce its occupancy. The heap occupancy remains at 1.27 gigabytes even after the full GC. This example shows that there are too many back-to-back full GCs happening, which is not good and it needs to be looked into. This log entry shows that the full GC took a long time to complete. So this was all about how GC logs can provide us more insight into the memory-related problems and what could be causing them. Heap dumps. Heap dumps are the most important diagnostic data for troubleshooting memory issues. These can be collected using JCMD, which is Java Diagnostic command, JMap, JConsole, Java Mission Control, and also by using the JVM option heap dump on out-of-memory error. This snapshot shows that we can use hotspot diagnostic mbean in JConsole to collect heap dump using its dump heap operation. I would also like to mention that this operation can be performed using any other JMX client. Heap dumps can be collected using the Java Mission Control as well. We can collect heap dumps using the heap dump on out-of-memory error option as well. This option enables the creation of heap dumps when the JVM throws out-of-memory error. However, we need to pay attention to a scenario where GC can continuously attempt to free up room on the heap by invoking back-to-back full GCs when the heap is almost full and the gains of these efforts are very little. These GCs delay the collection of the heap dump and the restart of the application and impact the application performance. We can use GC time limit and GC heap free limit options to avoid these continuous GC cycles. These options will cause the JVM to give up sooner and exit with out-of-memory error, with message GC overhead limit exceeded. GC time limit sets an upper limit on the amount of time that GCs can spend in percent of the total time. Its default value is 98% and decreasing this value reduces the amount of time that can be spent in the garbage collections. GC heap free limit sets a lower limit on the amount of space that should be free after the garbage collections, represented as percent of the maximum heap. Its default value is 2% and increasing this value means that more heap space should get reclaimed by the GCs. If 5 consecutive GCs are not able to keep the GC cost below GC time limit and were not able to free up GC heap free limit space, then an out-of-memory error exception is thrown. Alright, let's talk about heap histograms now. Heap histograms provide us a quick view of the objects present in the Java heap. Histograms can be collected by using the JVM option print class histogram and by sending sigquit signal to the Java process on Unix-like platforms or sigbreak on Windows platform. We can also use jcommand, jmap, jhsdb, which would be available in Java 9, and the diagnostic commands available in the Java Mission Control to generate heap histograms. This picture shows that we can use the gc.class_histogram diagnostic command to get the heap histogram in the Java Mission Control. Java flight recordings can be very helpful too in troubleshooting memory leaks. But one thing to remember here is that the flight recordings should be collected with the heap statistics enabled. How can we enable heap statistics? It can be done either in the Java Mission Control tool by going to Window Flight Recording Template Manager and selecting the option Heap Statistics, or by manually setting the Heap Statistics Enabled event to true in the Events Profile JFC file. Please note that enabling heap statistics can introduce additional performance overhead while flight recording data is being collected. This snapshot shows how heap statistics can be enabled in the template manager in the Java Mission Control. Now let's talk a bit about the next diagnostic data, Java flight recordings. How can we create Java flight recordings? Java flight recordings can be created using the JVM flight recorder options as shown here. Using Java Diagnostic command, JCMD with the jfr.start diagnostic command, with Java mission control by connecting to the process and then following the wizard to create the recordings. Please note that the flight recordings can help us find out the type of leaking objects. But to determine what is holding them in heap and causing them to leak, we require heap dumps. So far we have seen what data we should collect for diagnosing memory issues related to the Java heap. In this section, we'll take a look at the tools we can use to analyze that data and get to the bottom of memory problems. Let's see how we can analyze GC logs and which tools can help us with this analysis. So what do we want to look for in the GC logs? We want to see if there are too many full GCs occurring during the application execution, or if there are GCs with long pauses, or if the GCs are occurring too frequently. We can do the manual inspection of the logs and try to look for these problem signs there. Also, there are plenty of tools available that can do the visual and automatic analysis of GC logs. These tools are really helpful and effective in analyzing GC logs, presenting visual representations of heap usage, GC times, bytes reclaimed, and promotions, etc. These tools also offer great analytic insights into what could be going wrong and provide recommendations on how the observed problems can be avoided or fixed. This is the snapshot of a GC logs analysis tool, GC Viewer, showing an open G1 GC log file. Tools like these are very good at quickly pointing out anomalies in the application run. For example, in this case, it points out that with the G1 collector, there were two-space exhausted events, which are stop the word full GCs and are very expensive. In this case, these GCs took around 2 minutes each. Two-space exhausted GCs occur when there are not enough free regions available to copy the survivor objects from young regions too. We must tune the GC to avoid these full GCs and their negative performance impact. If we look closely at the other information provided by the analysis tool, we can see the initiating heap occupancy percentage, which is the heap occupancy at which the concurrent marking cycle starts. That will prepare old generation regions for the next evacuation pause. Reducing this percentage should help start the collection of old regions earlier, making evacuation pauses more effective. This should free up more space and avoid the two-space exhausted GC pauses. These are the corresponding GC log entries for the two-space exhausted collection. The important thing to remember here is that the two-space exhausted collections are stop the word collections. In this case, the pause lasted for 2.85 seconds, which is quite long. Sometimes the explicit GCs invoked either using system.gc or by using some diagnostic tool or command may be the cause for long pauses in the application. For example, the use of RMI can introduce GC pauses at the specified interval. These RMI pauses can be controlled by setting the GC interval properties as shown here. These explicit GCs are easy to spot in the GC logs. The GC log entries having system string in them are the full GCs that were invoked due to a system.gc call. The diagnostic tools and command can also introduce full GCs. An example of that is the print class histogram option, which can be used to collect per class heap statistics. When we send a sig break or sig quit signal to the JVM that's using this flag, it invokes a full GC before dumping the histogram information. So we should be paying close attention to whether the use of any diagnostic tool or flag might be causing full GCs in our application processes. To disable these explicit GCs, we can use the JVM option Disable Explicit GC. Heap dump analysis plays a key role in troubleshooting memory problems. Let's go over the tools that can be used for analyzing heap dumps. EclipseMath is a community-developed tool for analyzing heap dumps. It offers very useful features. It can inspect heap dumps for leak suspects, reporting the objects that are retaining large amount of heap. Math can show the object histograms. It can list the number of objects per class and heap held by those objects. It has an amazing capability with which it allows to include or exclude unreachable objects in its working set. So if we don't want to look at the objects that are unreachable and we are interested only in exploring the reachable objects, then this feature comes in very handy. This tool can also show the duplicate classes loaded by multiple class loaders. It can also show the reference chains to the GC roots, which are the objects kept alive by the JVM itself. It also allows us to use object query language, which is also known as OQL, to explore the objects in heap dumps. Its powerful OQL helps us in writing sophisticated queries that can dig deep into our heap dumps. JOverflow is an experimental plugin for Java Mission Control that enables us to perform heap dump analysis and get reports on where the memory might have been wasted. It's still in a premature state and can only perform very simple and basic analysis on heap dumps. Java Visual VM is an all-in-one tool for monitoring, profiling, and troubleshooting Java applications. It's available as a tool bundled with the JDK and can also be downloaded as a standalone tool from GitHub. Starting with JDK 9, it's no longer shipped as part of the JDK, and we encourage users to download it from its GitHub repository. One of its numerous capabilities is its ability to perform heap dump analysis. Visual VM can show class histograms, instances of a class, and can also help find the GC roots of particular instances. The JHAT is a web application that can be launched with the JHAT command, available in the JDK bin folder. JHAT enables us to browse heap dumps using our favorite web browser. JHAT supports pre-designed queries such as show all instances of a known class, as well as OQL, the object query language, that can be used to query heap dumps. Please note that from JDK 9, JHAT will no longer be shipped with the JDK. YourKit. It's a commercial Java profiling tool with a heap dump analyzer. One of its most outstanding features is its capability to not just list the reachable and unreachable objects, but the ability to distribute objects according to their reachability scope. For example, strongly reachable, weakly or softly reachable, or unreachable. Apart from having ad hoc query capabilities, YourKit offers a comprehensive set of built-in queries that can inspect the memory looking for anti-patterns. With these queries, YourKit provides causes and solutions for common memory problems. This snapshot shows a heap dump being analyzed in the Eclipse Memory Analyzer tool. The histogram in the snapshot shows that the instances of byte array occupy the largest portion of space. These instances are responsible for holding on to more than 406 megabytes of space in the Java heap. We can view the instances of byte array by right-clicking and selecting List Objects. This picture shows the list of instances of byte array that are responsible for growth in the Java heap usage. The tool allows us to get to the reference chain of objects responsible for keeping each of those byte array instances in memory. We can get to that information by right-clicking on a particular instance and clicking Merge Shortest Paths. It's better to get the GC paths without any weak or soft reference included, unless we are specifically trying to find the weak or soft references having any links to those objects. This picture shows that the byte array object being looked at is reachable from a vector, long-lived objects, in the memory leak class. This indicates that we should be looking at the source code of the memory leak class to understand why those byte array references are being stored in the vector object. In this section, we'll learn how Java flight recordings can help us in troubleshooting memory problems and what tools we can use to analyze Java flight recordings. Java Mission Control is a tool that can be used to analyze flight recordings. It's shipped with the JDK and is available in the JDK bin folder. Flight recordings collected with the Heap statistics enabled can greatly help us in understanding and troubleshooting memory problems. With Heap statistics enabled flight recordings in the Java Mission Control, we can see object statistics by clicking Memory Object Statistics. That will show the object histogram with the class names, count of their instances, their sizes, and the percentage of the Java heap those instances occupy. It also shows the top growers in the Java heap. This information is very useful as the top growers often are the leaking objects or have some relation with them. This snapshot shows the object statistics view in Java Mission Control. The heap content section shows the object histogram. The percent usage of heap by the instances of each class is a really good piece of information, as it provides a quick glimpse as to what is filling up the heap most. Top growers information is also very helpful. It shows the increase in the number and size of objects between the current and the last snapshot. In this case, we can see that the objects of byte array have grown in size more than the other objects. And that brings us to the end of this section. Thank you.